Okay guys, in this video we are going to continue our discussion of entropy um, by taking a look at the Carnot cycle. So this is more of the old school macroscopic approach to the second law, but it serves to highlight a few important points, and along the way we'll pick up a few ideas that are important in thermodynamics generally, as well as an important relationship that we'll use later on in the course called the Clausius Inequality. So the Carnot cycle it represents an idealized reversible heat engine. The significance of it being reversible is that it's going to generate the maximum amount of work that you can possibly get from an engine. And in our first, what we're going to do with the Carnot cycle is use it to show that entropy is a state function. And so in order to be a state function, the following mathematical relationship must be true. So this is inside here is the definition of entropy. ds equals dq over t for a reversible process. And then if you evaluate the change in the entropy over a closed path, that's what this little circle on the integral represents. If entropy were a state function, then this should be equal to 0. And so here's a diagram illustrating that. You've got your initial state of the system. It undergoes a change to some final state, and then the system returns to its initial state. So this is a closed path, thermodynamically speaking, and the change in any state function as you go around the closed path should be 0. Okay, and so if entropy is a state function, then the entropy, the sum of the entropy around the path, should be 0. So in order to prove that this is the case, we're going to use the Carnot cycle. And here's the conceptual argument. So the first step is to show that this statement is true for a perfect gas undergoing a Carnot cycle. And I'll go into what a Carnot cycle is on the next couple slides. Once you establish that this is true for the perfect gas, you then need to show that this is true for any working substance undergoing a Carnot cycle. And then once you've established that for the Carnot cycle, then you'll show that it's true generally for any arbitrary cycle. So this is the three logical steps in this argument that the entropy is a state function. We'll go through this first one in some detail, and then we'll get some interesting results after that, and then we'll return to these last 2 points closer to the end of the discussion. So here's what a Carnot cycle is. It's the simplest possible closed-loop path where each step is reversible. Okay, so we need to go around in a cycle, and we want all steps involved to be reversible. And the Carnot cycle is the easiest way to go about doing that. It consists of 4 stages. The first stage involves an isothermal reversible expansion. So you're going from some initial volume to a final volume at a particular temperature we'll call TH, the hot temperature. Then the next stage, you undergo an adiabatic reversible expansion. And recall from our previous discussions that when a gas undergoes an adiabatic expansion, it doesn't absorb any heat from the surroundings. And so as a consequence of that, as the gas does work on the surroundings, it loses energy and its temperature drops. So you go from this volume VB to a larger volume, but notice that the temperature also drops. Then we switch over to the compression stages. Stage 3 is an isothermal reversible compression, so you're stuck at TC, and then you'll go from some large volume VC to a smaller volume VD. After that, we have an adiabatic reversible compression. When you compress adiabatically, the system's temperature increases. So we start off at this volume VD, and then we go to the original volume VA, and we see that the temperature increases from the cold temperature to back to the original hot temperature. And so now we're at the same point that we were at the beginning. Okay, so it's a complete cycle. Let me illustrate that with this picture here. So here's our initial point. Stage 1, we follow an isothermal reversible expansion. Stage 2 is an adiabatic reversible expansion. So you're jumping from one isotherm here to another isotherm here by following this adiabat curve. Then we start compressing, going this way. So this is an isothermal compression at the cold temperature. And then we have an adiabatic compression back up to the original state. Here's another diagram illustrating that. It's essentially the same thing, although it does have the points labeled for us, A, B, C, and D. So what we want to do is then to calculate the entropy changes around this cycle. Now the first step is isothermal, okay, and so when you're evaluating the entropy change for that first leg of the cycle, you want to be using this definition, right? So just for the first stage, you would do something like this. You would want to integrate this. It's an isothermal path, and so when you do the first step from point A to point B, you're going to get the contribution to this first stage. I'll just call this delta S stage 1. When you do the integral, you're just going to get the heat for that, no integral. You're just going to get the heat that comes in from the hot reservoir, and you're at the hot reservoir's temperature. Okay, so that's why I have this first term here. You've essentially performed this integration for the first stage only. Now, the second term is 0. This is for the adiabatic expansion step. And since there's no heat flow and it's reversible, that means that there's no entropy change to the system. So if there's no heat, then it's 0. For the third step, again, it's an isothermal, it's a compression at this point. And so it's just the same format, only now we've got, our temperature is different, and then, the heat flow is going to be different as well. And that final step also has 0 entropy change associated with it because it's an adiabatic compression and there's no heat flow. So what we've gathered from looking at the Carnot cycle for an ideal gas is this is the result that we have so far. And then if we apply the techniques that we've been learning about for calculating heat for isothermal gas expansions, we would get these two expressions here. When you calculate the heat and divide it by the temperature, we get this relationship. Now, it looks like, why would you think that these two terms cancel out? You probably wouldn't think so just by looking at it. However, if you make use of the ideal gas adiabatic expansion laws that we've looked at previously, here's the one for the, I guess this would be for the first adiabatic, yes, this would be for the first adiabatic step, so this would be for stage 2, and this would be for stage 4. This would be for the compression. You can use these two equations to show that the ratio of VD over VC equals the ratio of VA over VB. And so if you make this substitution in here, you'll notice that this is VB over VA, this would be VA over VB. These two terms would be equal and opposite in sign. They cancel out. And so we've just shown that entropy is indeed a state function for the ideal gas Carnot cycle. On this slide, what we're going, and just to point out what's the significance of that, that was the first portion of our conceptual argument. So we've just shown that this was the case. Now I'm going to go on a little bit of a digression before we get back to these 2 points. We're going to talk about the efficiency of a heat engine. And so up on the left-hand side here, this is the definition of the efficiency of a heat engine. Okay, so eta is called the efficiency. It's a number that's going to vary between 0 and 1. 0 would be an engine that is completely inefficient, and then if eta is 1, then that would be a perfectly efficient engine, 100%. And so it's the ratio of the amount of work produced in the cycle divided by the amount of energy that's input from the hot reservoir. And so the amount of work that's done in the cycle is going to end up being the difference between the energy that's taken in by from the hot reservoir minus the energy that's discarded by the cold reservoir. And so you can substitute in for this work cycle, you can substitute in QH minus QC and then distribute the denominator here, and it gives you this expression for the efficiency in terms of the two heats. So this is the heat that's input into the engine itself, and then this is the heat that's discarded after the work has been done. You can show, again, using these formulas that we were playing around with. Okay, so just the formula for the heat involved in an isothermal expansion. You can plug in those expressions for the two heats, and you can show that eta is, the efficiency is 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. By definition, the hot reservoir always has a higher temperature than the cold reservoir, and so what we've shown here is that the efficiency is always less than 1, okay? Which means that you cannot convert heat into work with 100% efficiency. And I believe this was one of the Clausius, I think this was the Clausius statement of the, or maybe it was the Kelvin statement of the second law. I don't remember which one. It's one of those two statements. An interesting side fact, okay, you probably have heard of the idea of a perpetual motion machine. There's two kinds. They're both impossible. A perpetual motion machine of the first kind is one that would create energy from nothing, which would be a violation of the first law of thermodynamics, which tells you that you cannot create or destroy energy. You can only move it around. A perpetual motion of the second kind would be some type of engine that can convert heat into, that can convert 100% of heat into work, which we've just shown that this is not the case. This would be a violation of the second law of thermodynamics. This is the diagram of a heat engine. We've looked at this before in probably the last talk. So here's the idea, right? You've got a hot source and a cold source. So an amount of energy is absorbed by the working substance, 20 joules in this case. Some of that energy is used to do work, so 5 kilojoules is lost as work, and then the remaining 15 joules needs to be discarded into the cold reservoir in order to reset the engine so that you can start the cycle over. Okay, what we've shown is that you cannot convert all 20 joules into work. You always have to deposit some energy into the cold sink in order to reset the engine. So here we've just got a couple of fun little problems thinking about heat engines. So in this case, we have a heat engine that's running according to the Carnot cycle. in which 100 joules of energy is withdrawn from the hot source. And so QH is equal to 100 joules. And the temperature of the hot source is 500 Kelvin. Some of that energy is used to do work, and some of that energy is deposited into the cold reservoir, which is operating at a temperature of 300 Kelvin. And so we're being asked to calculate the amount of energy that is used to do work, and calculate the amount of energy that is used that is deposited into the cold reservoir. Well, the first thing that we can do is to calculate the efficiency of the engine. And so if you take 1 minus 300 divided by 500, you get an efficiency of 0.4, so 40% efficient. And then using the relationship that the efficiency is by definition the work that's done on the cycle divided by the amount of heat that's absorbed from the hot reservoir, you would get that the work done is just going to be the efficiency times QH. And so since QH is 100 joules times 0.4, it's 40 joules. So with this particular engine, with these two temperatures, you can do 40 kilojoules, 40 joules of work. And then the heat that's lost to the cold reservoir is going to be that QH minus the work that was done. So that's going to be 60 joules. 60 joules is lost. This problem is straightforward. They give you the they're talking about a power station that uses superheated steam and discharges some waste heat into the environment. They give you the two temperatures, calculate the efficiency. You just need to use this formula right here. So you take 1 minus Tc divided by Th, and that'll give you the efficiency for this problem. Okay, well, that's the end of our digression, and so what we'll return to next is to set about proving that entropy is a state function. And so we've shown that entropy is a state function for an ideal gas in a Carnot cycle. The next step is to explain that the entropy is a state function for any type of Carnot cycle, regardless of what the working substance of the engine is. And so that we can make that argument using this diagram here, where we have two heat engines working together between the same two thermal reservoirs. So we have engines A and B, and for argument's sake, we're going to assume that engine A is more efficient than engine B. And so engine A is going to absorb some heat from the hot reservoir, and it's going to do some work, and it's going to deposit an amount of heat QC into the cold reservoir. Now, the work that is being done by engine A is going to be used to run engine B in reverse. That is, it's going to force engine B to absorb QC energy, as heat from the cold reservoir, and then engine B will then deposit some energy into the hot reservoir. Now, you might think that's fine. However, because supposedly engine A is more efficient than engine B, some of the, essentially engine A will be able to generate more work than is required in order to transfer this amount of heat from the cold sink into the working substance. Okay, and so effectively, if this engine is more efficient than that engine, effectively what it means is that you can then generate excess work, without depositing any energy into the cold sink. Notice that engine A is depositing some energy into the cold sink, and then engine B is pulling that energy right back out, using the work that engine A had derived. And that's effectively the same as saying that you can do work using 100% of the heat, of an amount of heat, and that violates the second law. And so the conclusion is that the assumption that engine A and engine B operating between the same two thermal reservoirs would have different efficiencies is false. Okay, so you can't have, there's no distinction between the two heat engines, which means that all engines, regardless of working substance, will have the same efficiency. Correspondingly, the entropy around the closed path for any engine operating in a Carnot cycle would then be a state function. It's a little complicated at this point. The last portion is a bit easier to understand, graphically at least. The next step and final step is to show that any arbitrary cyclic path, not necessarily a Carnot cycle, that the entropy change around that path is zero. So you don't necessarily have to be confined to a Carnot cycle. Any cyclic path for any heat engine would have the entropy as a state function. And the way that this can be understood is that an arbitrary cyclic path can be approximated by a set of overlapping Carnot cycles. And so here we have these red curves. So this would be an arbitrary cyclic path. You can represent this overall path, which is arbitrary, by any number of Carnot cycles. And so here we're representing it by 3 Carnot cycles. And so if the entropy change around each Carnot cycle is 0, then that would mean that the entropy change around this arbitrary cycle would be 0. And so for any cycle that you want to make, you can always decompose it into smaller and smaller Carnot cycles. Hence, delta S equals 0. The sum of delta S equals 0 for all, I should say ds, for all closed loop cycles, which means that S is always a state function. And so that's what we set out to show. The last couple of slides deal with something called the Clausius inequality. I won't bother to prove it explicitly just because it's a bit involved. It's not too bad. It's just it'll make the video a lot longer. I just want to point it out. The Clausius inequality holds for any irreversible spontaneous process. And so here what we're saying is that ds is greater than or equal to 0. Greater than or equal to the ratio of the actual heat, the infinitesimal heat divided by the temperature. Recall from the definition of entropy that the definition of entropy is that ds is equal to dq over t for the reversible path, for an irreversible path, dq, the Clausius inequality holds, and so ds is greater than or equal to the actual heat divided by the temperature. And you can use this to justify various various aspects of the second law. We don't really need to get into that too much. I'll just point out a few of the more important important aspects. First, one thing that you can conclude from analyzing this equation is that the entropy always increases for a spontaneous process when you have an isolated system. So and that isolated system could be the entire universe itself, which is consistent with the second law. Or if you just have your system and it's well insulated and it's closed, then, and if a chemical reaction occurs or something like that, a physical reaction of some sort, you know that the entropy of the system increases. As long as it's shut off from the surroundings and can't exchange heat with the surroundings, you would know that it's a spontaneous process. It also, it also distinguishes between reversible processes and irreversible processes. So the greater than symbol is for the irreversible path, and then the equality, the equal part, is the case for the reversible path. And so reversible processes aren't technically spontaneous because the system is already at equilibrium by definition. All spontaneous processes are in fact irreversible processes. Finally, what you can show from that is, I think this was the Kelvin statement of the second law, that heat spontaneously flows from hot objects to cold objects, and that's represented by this diagram right here. So here you've got a hot source. It's in contact with some cold thermal reservoir. You can calculate the entropy change associated with transferring some heat from the hot source to the cold source. Okay, its ds will be equal to negative dq divided by the temperature. So when heat is transferred from the hot object to the cold object, this system, this subsystem, loses entropy. Okay, so the entropy of the hot source is going to decrease when it transfers energy out as heat. The entropy of the cold reservoir is going to increase when it accepts the heat. Okay, and the entropy change associated with the cold object is ds equals dq over tc. Notice they're equal and opposite signs, right? The hot object loses entropy, the cold subsystem gains entropy. And the same heat is involved in both cases, so the magnitude of the heat is involved. So they're equal and opposite in sign, at least the numerator is equal and opposite in sign, but the denominators are different, right? The hot object has a higher temperature by definition than the cold object. So as a consequence of that, the entropy increase associated with the cold object is larger in magnitude than the entropy decrease associated with the hot object. And so when you add the two entropy changes together, there's a net gain in entropy overall. Okay? So whenever heat transfers from a hot object to a cold object, the overall entropy increases, as is consistent with the second law and the idea that heat flows from hot objects to cold objects and not the other way around, at least when it's a spontaneous transfer of energy. Well, with that, I'm going to go ahead and stop this video, and we'll pick up with the next topic, where we're going to look at calculating entropy changes for specific problems.